So what are you guys?
We're the Swartwood family!
Hey guys, so we're going to do a follow-up continuation video. And we're going to do something that I think is relatively rare because I don't think a lot of people talk about this modified version of pi. Okay, so what's pi? So it's a principle of inclusion and exclusion. This video definitely assumes that, especially the approach we're going to take, that you've seen the previous video. So if not, if you just look for Swartwoodprep and you look for basically the principle of inclusion and exclusion, it should come up. Okay, so that video, I think it's called like a proof. Okay, so it's a proof of the inclusion and exclusion principle or something like that. That's what you want. So if you're comfortable with that and the ideas from that, then this will follow pretty smoothly. So unlike most of the videos, even though I will do a lot from scratch, I'll assume that you are comfortable with that video. Okay? All right, so pi is slightly more generalized version. So first, what's the idea? So this part we're definitely going to do from scratch. Let's say we have 3 sets here. Okay? And let's say we have something like this. So what we do with pi is we count the number of guys that are in basically this whole thing, right? Okay, but the version we're going to look at now is slightly different. It's going to be a little more precise. We're going to pick any number of intersections. So let me rephrase that. We're going to pick any number of sets. Let's say 2, okay? So what we're going to say is how many guys are there that are exactly in the intersection of 2 sets? So what I mean by that is this guy doesn't count because he's only in 1 set, okay? These guys right here, they count. Because if you look right here, they're in the intersection of exactly 2 guys. But these guys right here, they don't count. Because they're an intersection of 1, 2, 3 guys. Does that make sense? All right. So we need a name for that. I'm going to call it, for example, like A2. That's going to be my notation. So something like this, A2, it's going to be the number of elements in exactly 2 sets. Okay? So a lot of textbooks that talk about this or they deal with this, generally they talk about this in terms of properties. So it starts to become more abstract and you think of properties, et cetera, et cetera. But you can think about, well, you can think of it this way. Being or having a certain property is basically equivalent to being in a set, right? So this could be like property 1, property 2, property 3, right? Okay, so I'm just going to do this in terms of sets. No big deal. All right, so we need a little bit more notation too. Okay, so I'm going to start using notation like this, S1, S2, S3. And let me show you why. So do you remember the regular principle of inclusion and exclusion for 3 sets? It kind of looked like this. The magnitude of A plus the magnitude of B minus the magnitude of the... So when I say magnitude, I really mean the size of the set. Okay, it's my shorthand. The intersection minus this intersection minus this intersection, right? Plus this guy. Now I'm doing this pretty quickly, but I'm assuming you're comfortable with that previous video. Okay, so this thing right here was figuring out or computed all the guys are in there, right? Okay, but the way we did it was we first, oh, I'm on crack. There we go. Okay, all right, so let's redo that. So notice here we added up, right, the number of guys in each set, right? So A plus B plus C. So we'll call this S1. So this entire sum. Okay? And then notice here, we added up, well, excluding the negative sign. Let's write it like this, right? So we're going to subtract this guy and that guy. So we're subtracting the sum of all the double intersections. So we'll call that S2, okay? And then here, there's only 1 guy. But you can imagine if there were more triple intersections, we'd sum them all up. With this sort of notation, it's going to be much more efficient, especially for the formula that comes with this guy, rather than writing them all out, okay? What we want is we want something like this. So in general, if we have like a bunch of sets, right? Some of them intersecting, some of them not, blah, blah, blah. If you want a number of guys in the union of all those sets, you'd use regular old pi, and there's nothing wrong with that. So let's say you have that big union, right? And now you want to know the number of guys where each guy's in exactly 2 sets, okay? So for example, A2, okay? Now, of course, in general, we're going to go for a formula for AK. And you can look up the formula, use it, and apply it. That's great. But the point of this is to basically give you the intuition behind this guy, the proof of this guy, like where it comes from, right? And I think what's going to be a little different here is we're going to talk about like motivation. So if you're just sitting around your own, like how could you come up with this, okay? So again, you might want to try it on your own, come up with your own way of doing it. I just wanted to share this because we had a request, and I think it's kind of interesting to talk about. So let's try with this though. Let's say you have 5 sets. And we're looking at the union of 5 sets, okay? And let's say, aside from that, we have, well, we want to look at A2, which is the number of elements that are in exactly 2 sets, okay? So again, it doesn't have to be the same two sets. So if we had 5 guys that look like this, 1, 2, maybe 3 here, 4, and like 5, right? We want the guys that are saying here, exactly in 2 sets, exactly in 2 sets. All right, so let's try this intuitively. Well, first, my gut instinct would be, like we did with the general principle of inclusion and exclusion, let's just sum up all the double intersections. We're not going to start with S1 because we're looking for guys that are exactly in the intersection of 2 sets, right? So there's no point in counting guys that are just in, you know, like here, right? So we're going to ignore that. So we're going to ignore where we count guys that are in 1 set, okay? Plus, it adds a little bit more complexity because technically when you do S1, if you have a guy, I don't know why I just erased it, right there, right? Then you're going to count him once for this set and once for that set. So I think it's just much simpler if we start off by just looking at the guys that are literally in the intersection of 2 sets. And if that's all you had, if you just had like something like this, and maybe over here something like that, and something like that, you can just compute this number and you'd be done. The problem is that if you have guys that are in triple intersections, then, like we saw before, elements here are totally fine. But guys that are in the triple intersection, they're going to be overcounted. The other thing is that we don't want to count guys in the triple intersection. Remember that? We want them to be exactly in 2 sets. But anything in the triple intersection would be exactly in 3, right? But at this point, it might be a little confusing because you might be thinking, doesn't this count the number of guys that are in double intersections? Yeah, it does, but remember, this is literally you take any intersection between 2 guys, which includes all of this region, so everything in here. And you literally add them up. So for this and this, you would count 1, 2, 3. But then for this and this, you would count 1, 2, 3. So it doesn't give you exactly the number in double intersections. It just gives you double intersections or more. So it doesn't give you the guys that are just purely in double intersections like this. It gives you guys that are in any sort of double intersection, whether that includes guys that are also in triple intersections, quadruple intersections, quintuple, et cetera, et cetera. So counting guys like this, which are definitely in here, are good. Counting guys like this, which are also in here, are not so good. So we want to fix it, right? So I think one natural thing to do would be kind of like before, take out all the guys that are in triple intersections. So this guy counts guys that are in triple intersections or possibly higher intersections. And if you compute this guy, you take this guy, subtract out this guy, then you're removing, at least in this case, all the guys that are an issue. Okay? All right, so let's see. So for example, if we had 1 here, 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 and 2 there, what does this guy count? This guy counts, say, this intersection 1 time. So it would count 3. And then it would count this one. So it would count 3. And then it would count this one, okay? Which would count 3. And we'd have 9, okay? It's clearly not what we want because we know that we want this, this, and this, and that's going to be 3. Okay, so I think if we subtract this off, we'd be in a better place. So you look at the guys in the triple intersections. So we subtract off 2, right? And then we've gotten almost what we want. Well, at least better. 7's closer to 3 than 9 is. Okay, so what was the problem here? Remember, there are 2 issues going on. Number 1, you don't want guys in the triple intersection to count. But number 2, every time you were adding up the double intersections, you counted this guy. You didn't count him just once. You counted him 1, 2, 3 times. Does everybody see that? So maybe we can fix it if we take that 9 and we subtract off this overcount of 2. But how many times did we overcount this guy? 3 times. So then that would be 9 minus 6. That is 3. That is what we want. So that's roughly the idea. So you're playing with this and you're like, okay, I get it. You take the double intersection type guys, that's sum, S2. You subtract off S3, at least in this simple case, and we can kind of see the pattern's got the right idea. There are 2 problems with this. Number 1 is every time you're counting this too many times. So we've got to have some factor in front to compensate. In this case, it's not that bad. It might get slightly more complicated with more sets, right? The other issue that we're kind of forgetting here is, what if there was a quadruple intersection, right? Just like when we're doing regular pi, then it's kind of like we're kind of overestimating the number of triples in a way, right? Because with every quadruple, you have a bunch of triples that would come from that quadruple. When 4 sets intersect, right, you'd have 4 sets out there. There are 4 choose 3, or 4 ways of picking out triplets. So when you have a quadruple intersection, any element in the quadruple intersection is effectively counted, if you count by triplets, 4 times. Okay? Don't worry about that. We'll go through it more slowly. I just want to outline this idea. You've got two issues going on. Number one, we want to correct S2 by taking out S3, but we're kind of overcounting, so we need to fix that. The second issue is, if you had greater intersections, then maybe this estimate is also sort of overdoing it, right? So we compensate by adding back. You saw that from pi. You subtract, you add, you subtract, you add, okay? We could keep progressing forward like this, but it gets kind of tricky. The other thing is sometimes what people do when they prove this stuff is they start with the formula. You start with the formula and then you try to prove why it's true. And that's okay, and it's not too bad. But the thing is, I think, at least for me, the idea would be like, where would you come up with this to begin with? I personally think that's more important. I mean, it's great to prove it once you have it, and that's super significant. But at the same time, like if you don't even have a formula to begin with, right, then there's nothing to do. So what we want to do is this. We want to basically do the same thing with this understanding, but I just want to focus on what we're counting, okay? So if we have a guy that's only in a double intersection, like an individual element that's only a double intersection, he's counted here, he's just fine. The problem arises when, for example, in the previous case, you've got a guy that's in a triple intersection. And because of that, he appears in multiple double intersections, right? So that's why we're going to try to adjust by taking out that triple, right? But like you saw in this case, that guy is counted multiple times. Does everybody see that? Okay, so what's a way of sort of fixing this? Why don't we visualize it like this? Take any element. Actually, first, let's do it 5 sets, okay? And do you agree we're going to pick out one element? So we saw that in the proof of pi. Right? You can focus on one element to make the argument simpler. So we're going to think about what's happening with one element. Now we need to place him somewhere. So could this one element be in the intersection of all 5 sets? Sure. But just to make a point, let's make this guy in the intersection of 4 sets exactly. So let's make this one element, let's call it alpha. Let's say it's in the intersection, well, let's do this. Let's say there's A1, A2, A3, A4, and A5 will be the final guy, but we won't use A5. We won't even go all the way up. Just trying to make a point. Okay? So let's say alpha is in the intersection of 4 of those guys. So alpha sits exactly in 4 of those guys. Okay, so now the first thing, if we're counting the number of guys that are exactly in 2 sets, would alpha belong there? And the answer is no, right? So you're looking for guys that are exactly in the intersection of 2 sets. But this guy, alpha, he sits in the intersection of 4 guys. So if we're counting this right, alpha should not appear in this answer, because he doesn't belong to just 2 sets, he belongs to 4. Does that make sense? So guys that are legal over here would be guys that are just in alpha 1 and alpha 2, or say alpha 3 and alpha 4, or alpha 1 and alpha 4, stuff like that, but not alpha 1, 2, 3, and 4. So what we're going to hope to do is, over here, we're going to set it up so you don't see alpha. You count them literally 0 times. Okay? All right, so what's one way of doing this? We got this element alpha, and since we're always talking about intersections of 2 sets, right? I think a key idea that's intuitive, at least to me, is before we look at an element and we're just looking at how many times it's counted. But now let's look at an element and when he sits in a pair, an intersection of sets. So we're going to count all the different double intersections he can kind of sit in. Okay? All right, well, wherever alpha is, S2 would definitely count all the double intersections he could sit in. But now, here's the thing. How many double intersections does he sit in? Well, if you have 4 guys, 1, 2, 3, 4, right? He sits in the intersection of A1, A2. Right? A3, A4, A1. So basically any pair from here works. But you know how to count that. That's going to be 4, choose 2. There are 4, choose 2 ways to pick out any pair over here, right? And if you're sitting in one of these pairs, like A1, A2, alpha definitely sits in there. It would be counted once over here, right? Because this guy literally counts all these double intersections. Everybody in there, actually. But how many times is alpha counted in this guy? He's counted once. He's counted once for here, once for here, et cetera, et cetera. So it looks like you're going to have 4 choose 2 double intersections that alpha sits in, and each time he's counted once. So this is the number of times we counted alpha. Okay, so obviously you want this to be 0, so you're going to subtract something out. Okay. But now when you think about the triple intersections, so let's think about it this way. First, let's start off with a similar idea that I think is very natural. What we did was we saw how many double intersections alpha sat in, right? Okay, now think about this. Since alpha sits in 4 sets, right? First, how many triple intersections are there, period? So if you look at this, it looks like, well, I think there's 4 choose 3 triple intersections. So I'm going to put that over here. Does everybody see that? There are 4 choose 3 triple intersections that alpha sits in. So right there. Okay? Now, I know right now it's a little deceptive. We're just going with this general theme, and then we'll clean it up. Okay, but the story's not done, because when we look in here, this is the number of triple intersections. That alpha sits in, right? Okay, what we've counted here is the number of triples that alpha sits in, but that's not what I want. What I want to do is I want to sit there and basically count the number of double intersections alpha sits in. Okay, well, there are 4, choose 3. There are 4 triple intersections. But for each triple intersection, how many pairs can you pick out? Well, in a triple intersection, there are 3 guys, right? And you're going to pick out 2. Does everybody see that? All right, so what's our game plan? So how would you come up with this crud? It's going to be like this. The idea is we are basically trying to count everything in terms of pairs. So intersecting pairs like this. So one way to do it via S2 is you just count them out. There are only 4 choose 2 pairs, right, that alpha sits in. So that's what we counted in here. Okay, what about in here? Well, in here, this guy adds up all the triple intersections, not just the ones containing alpha. But if we're focusing on alpha, right, in this sum, you will see 4 choose 3 triple intersections that you're going to be counting here, right? And for each triple intersection, you're counting alpha once, because you're sitting in that triple intersection. Okay, that's totally fine. So really what we're doing here is we're making use of this, how alpha belongs in there. But again, we're arguing by pairs. So really what I want to do is I want to say, okay, there are this many triple intersections that are counted for here. But what I really want to do is count the number of pairs. So for every triple intersection, you have 3 choose 2 pairs. Does that make sense? Okay, then we're basically recounting all the pairs again, but we're doing it from the point of view of triple intersections. So you take a triple intersection, count all the pairs from there. Okay? Does everybody see the big idea? Sorry, I don't want to beat this to death, but I'm really saying it because I think once you have that big idea, then the rest of it's very mechanical. But the big idea is here you're just counting out pairs, period. Here you're counting out pairs, but in a different way. First you look at the number of triples, and then the pairs that belong to those triples. Then, over here, we're going to run it all the way. Because general inclusion, exclusion, we might be overcounting, right? So now we're going to look at all the quadruple intersections. Hi guys, you might be wondering about the costume change. Sorry, but the camera actually ran out. So it ran out of charge last time. This time we're a little bit better prepared, so I'm going to go ahead and finish, okay? But at least we did the setup. So the setup was something like this. And remember, the main point here is to think about what's the inspiration, how would you come up with this, okay? So our idea was this. It isn't just that you're looking at double intersections and triple and quadruple. Then it'd be like, where did these coefficients come from? It's, you want to visualize it like you're actually counting all the double intersections, just different ways. Here, just straight up, it's going to be the right number, right? Then here, do it in terms of triples and the doubles you get from the triples, and that will be overcounting, okay? And we're going to make an adjustment, or we're going to check that when we do all this, it's going to work out just fine. Over here, it's pretty mellow, right? If you're sitting in 4 sets, then how many quadruple intersections are you sitting in? Just 1. Because you have to choose all 4 of those sets, right? So it's going to be 4 choose 4, 1. Because remember, these are literally all the sets that alpha sits in. But then for every quadruple intersection, again, the same procedure. How many double intersections is alpha going to sit in? Well, that's going to be 4 choose 2. Now you might be like, well, this is kind of lame, because here you counted it right, here you overcounted, and here you kind of count it right, because you end up getting the same number, right? But that's not the main idea. The main idea is even when this gets more complicated, the procedure remains the same. Right now it's double intersections, but it could have been triple, quadruple, quintuple, whatever, okay? But the idea is whatever your target number is, right? We're going to count those sorts of intersections. And we're going to do it just first straight up. Then we're going to take bigger collections and then generate from them. And then bigger groups over here and generate from that, okay? So it's just, in this case, to be concrete, we're counting the number of double intersections that alpha sits in. We're doing it straight up. Then we're kind of doing it sloppy. We're doing first the triples you can get from the possible guys out there, and then the doubles generated from them, and then the quadruples and the doubles generated from them, et cetera, et cetera. Okay, that's the idea. All right, so now, and by the way, these are actually the coefficients, so that's the inspiration. So the way you should view it is, those coefficients come from this idea of, let's count all the double intersections that alpha sits in, because that's what we care about. We're just going to do it different ways, okay? But then you're thinking about, okay, well, we do the whole thing, subtract and add and so on, right? How do we know then that this is going to count it right? Because my claim is we're actually done. This is it. All right, well, let's say this. If alpha only sits in a double intersection, then it wouldn't be in a triple, quadruple, so all of these would be gone, right? It'd be in one double intersection, so you'd count it one time. And of course, it'd be counted once here because it'd be an element that only belongs to 2 sets, okay? All right, but now, like this hypothetical case, alpha belongs to 4. So should that count on the left? No, because the left counts only the guys that sit in double intersections. But alpha actually sits in a quadruple intersection, right? So on the left, alpha should be counted 0 times. But of course, if you sit in a quadruple intersection, you also sit in double intersections. So what we're doing is we're counting those guys up, and we're hoping that when we count it, everything will go to 0. Okay, so let's see that. First, this is actually the number of double intersections that alpha sits in. That is actually the correct number. And if you imagine these guys like, let's do that. A1, A2, A1, A3, A1, A4, A2, A3, A2, A4, and A3, A4. If we did it right, there should be 6 of them. Yeah, these are all the double intersections that alpha sits in. And that's the correct number. Okay, but now over here. Over here, we looked at the triple intersections. So that could be A1, A2, A3. It could be A1, A3, A4. It could be A2. Oh, shoot. My bad. I forgot the video is truncated here. So I'm going to go ahead and do it like this so you can see everything. Okay, anyway, hopefully that's the same. I said it correctly, it's just you probably couldn't see it on the screen. So there you go. All right, so let's go for this. A1, A2, A4. So my apologies if I miscounted, but I think these should be all the triple intersections we can pull out. Okay? All right. Now, it stands to reason that if you take all 4 and you pull all the doubles from them, we're going to get exactly the same guys over here. Okay, but anyway, the main argument is going to be from this. So how is this going to work? And these are the number of double intersections alpha sits in. So this is the right number. So if we count this up and we subtract it out, then we should get 0, and that's what we want. Okay, obviously when we're counting here, we're going to see in a second, we can overcount. Now we could write all this crud out, but that's a pain. So what I want to do is I want to focus on what happens with each individual guy. Let's focus on this guy. Well, first, do you guys agree? From these triples, when you pull doubles from them, you're going to get every single one of these. That's not the problem. But we've overcounted because sometimes guys over here, like A1, A2, will count multiple times on the right. Okay? So how can this happen? How many ways are we going to overcount? For example, if we look at this guy, A1, A2. Well, if you're pulling doubles from these guys, in order to get A1, A2, you have to contain A1, A2. So that one works. This one does not work because you can't get A2 anywhere from this. So we're going to ignore him for the moment. Let's see. Over here, nope. Over here, yes. Okay? And then when we compute the doubles we can pull from this, we're going to end up getting, so from this we can definitely get A1, A2. Okay? We can also get, let's see, A1, A3, and A2, A3. Okay? All right. Over here, what can we get? We can end up getting A1, A2, A1, A4, and A2, A4. Okay. All right, does everybody agree? These are the guys that we can pull? Okay, but my argument is going to be, and so clearly we're going to get everybody, but we're going to overcount. I want to focus on this guy, how we're overcounting this guy, because this argument will hold up for any of these double intersections. Okay, let's look at A1, A2. We see it here and here. So we're going to overcount twice. So we're looking for a general pattern, so let's actually count. Let's count this out. So the thing is that over when we look at the triples, it could be the case that different triples will generate A1, A2. From a given triple, we're not going to generate A1, A2 more than once, right? If you have 3 guys and you're pulling 2, like A1, A2 specifically, there's only one way to do that. But you may have different triples that when we pull pairs from them, we're going to end up with the same guy, and that's overcounting. But in order in general to have a triple that's going to end up giving us this pair, A1, A2, you have to have A1, A2 in that triple, right? But that means that the thing in the third position could be anything, right? Anything that's legal, any of these sets that contains alpha. So how many ways are there of doing this? Well, let's see. All right. We have 4 guys out there that contain alpha. A1, A2 are fixed. We don't have a choice about that. So if you pull out A1, A2, there are 2 guys left. Okay? Of those 2 guys, you can pull 1 or put 1 in that position. So it's 2 choose 1. Okay? And it's clear if you just count this out, this is alpha A1, A2, and A3, or A1, A2, and A4. Okay, so that's it. So it looks like for A1, A2, we've overcounted 2 choose 1 times. But that holds up, if you think about it for a sec, for every one of these. Okay? So this guy is overcounted 2 choose 1 times. Okay? All right, but now, what about over here? Let's try to do the same thing. Well, this one's going to be pretty mellow. What ends up happening is we take a quadruple guy there, right? And we want to know, well, in this case, it doesn't really matter because there's only one quadruple thing. But let's just think it out in case. If you had a quadruple guy and you want to pull 2 of them, right? What is the requirement? Well, in order to contain, let's do the same argument, A1 and A2. We're going to focus on that. Then that means we have to include in our quadruple A1 and A2. Okay? So those guys remain fixed And now we need to fill in 2 slots. Okay, so if you pick A1 and A2, that not only is A3 and A4 in the running, but you needed to choose 2 guys to put in there. So out of the 2 options, you've got to choose 2. And that, of course, is going to lead you to 1. But you know that because there's only 1 quadruple out there in this case. But you see how the pattern will hold up in general? Okay, so let me get this straight. Oh, and how about over here? Well, over here, we know we're going to count it correctly 1 time. So you can think of it like this. Here, it's definitely going to be 1 time. You count that double 1 time correctly. But to keep the pattern up, you can think of it like this. You pull that double, A1, A2. Okay, how many more do you need to fill in? Well, you're only looking at doubles over here, so you're done. So if you pull out A1 and A2 to be in your double, how many guys are left? There's still 2 guys, A3, A4. But how many of them do you need for that double? You need nothing. So it's going to be 0. Does everybody see that? It's like if you have A1 and A2, there are 2 guys left, A3 and A4, but you're going to pull none from there because you've got your parent. But for triples, you put down A1 and A2, there are 2 guys left, and you're going to pull what? You're going to pull 1 more to finish the triple. And over here, you have what? A1, A2, right? 2 guys out there, and you're going to pull both of them to finish that quadruple. Okay? All right, doesn't look so bad, so I think we're going to be able to finish here. So let me clean this up, 1 more line. So really the argument becomes, so 2 choose 0 minus 2 choose 1 plus 2 choose 2. And now we use what we did in the previous proof, the general proof of pi. Remember the general proof of pi, if you sum some guy from n choose k, -1 to the k, 0, up to n. We did this already. That's going to be 0. And that's exactly this pattern. So we have the top fix of 2, and we run them from positive with 0 up to -1, positive 2, like that. This will definitely sum to 0. So the right-hand side counts 0, the left-hand side counts 0. We know we're good. Does everybody buy that? So now we're going to do the same thing. Now it's just, now that we have the idea and we have the inspiration, that was the key point of this. Where did these guys come from? It's not that bad to do it in general. And I'm going to say this in words. So now we're looking at, let's say there are n sets involved, and we want the number of exactly k intersections. So if that's the case, where should you start? You should start at sk. Okay. And then you should subtract off, but now we're going to count now, instead of in pairs or double intersections, we're going to count in k intersections. Okay. So we want the k intersections. The next guy up are k plus 1 intersections, right? So you're looking at, out of the k plus 1 guys, you can choose k of them to be a k intersection. Okay? Does that make sense? So if you look, this totally matches what we did before. And now we're going to add, so let's say it's sk plus 2. Oops, need room. Okay, there are k plus 2 guys. We're going to choose k of them, right, for those k intersections. And then we're going to go all the way up. So let's do the generic one. So whatever the sign might be here. sk plus, let's say, m. Okay? And then we're going to have over here, let me see. Sorry. Somewhere along the chain here, we're going to have, let's say, k plus m. I want to choose k of them, right? Okay. Right, it's going to have this pattern. We'll figure out the sign in a second. It's not a big deal. And then we keep going. What's the final term going to look like? We're going all the way up to Sn, even though we might not need to use it. So we're going to look at this guy, and it's going to be n guys. We're going to choose k of them. Again. Okay, so what about this -1? That's more like bookkeeping. The main idea was getting those coefficients, but we could do it now. Let's see. So if n were actually k, then you want the guy to be positive. So I think maybe, let's try this. Let's try n minus k. We could talk about where this comes from, but this is just playing with flipping the signs. It's not the main point of this, but let's just test this idea out. If n were, say, because what's happening is you're alternating positive, negative, positive like this. And whether you stop here or you keep going depends on how many terms there are. So I'm going to take the difference to get the number of terms. Okay? But now, if n were actually k, that's all we're doing, then it would be -1 to the k minus k. But then that would end up being what? -1 to 0, which is +1. That works. What if we ended up going to here? Then it would be, well, n is k plus 1, and you're going to subtract off k, that would give you 1. -1 to the 1 is going to be a negative, and that works too. So this power right here totally works out. Let me know in the comments if you want to talk more about that. But again, that's kind of peripheral to what we're really going for. So I want to go for this pattern. So here's our basically complete proof, just a little bit mellow and kind of informal. But the same idea. You look at an element alpha. And alpha might be an intersection of, let's say, m sets. Okay? And you could designate them. For example, you might designate them alpha I, this is where it gets really tedious, 1 up to, AI1 up to AIM. assuming that your sets are labeled, say, A1 to AN. The reason why I'm putting the I here is it doesn't have to be A1, it might be A2, but we're saying there's M of them. Okay? Again, that's not so important. The main point to pick up here is that alpha is in M sets, exactly. Well, if an alpha is in M sets, and of course I'm going to assume M is greater than K. Okay? If M is equal to K, then it's in the intersection of exactly K sets. It's counted once here, it should be counted once there, and none of these other terms even apply because it's in K sets, not K plus 1 or K plus 2 or K plus 10, right? The only issue is when you're out there and this guy is greater than K. Okay. Oh, my bad. I don't want to confuse anyone. I don't mean that that M is the same as this M. I just want to give some arbitrary guy here, and I thought M was a good letter, so let's go with that. Okay? All right, my bad. We can always come back and do it more cleanly if you want, but I think the main point is just to get this idea out there. Okay, so we have this set up here. Now, if M is greater than K, that means it's in the intersection of M sets. So it's not in exactly K sets, so it doesn't belong. So on the left-hand side, it would be counted 0 times. Now the question is, how many times would it be counted on the right? Hopefully it's going to be 0. Okay? All right, but in the K guys here, right, in the K intersections, well, if you're in exactly M sets, right, then it's a fact that you'll be in M choose K intersections. Because that's how we get all the K intersections that contain this guy alpha. It's literally you take your M guys and you pull out K of them. Okay? Now let's go to here. Now we're actually going to put in this coefficient we've artificially constructed. Okay? Okay, so now what about K plus 1? Well, again, what's going on? If you look at the K plus 1 intersections that contain alpha, how many of them are there out there? Well, alpha sits in M guys, right? So alpha sits in M sets. And so you're generating all the K plus 1 intersections by taking K plus 1 guys from that M. So this is just like before when we're doing the whole like triple intersections, right? How many doubles do you get from that? 3 choose 2. Let's do a couple more to make sure we're good. So I'm just copying down this coefficient. I'm going to think about this. If you have K plus 2, and how many K plus 2 intersections can you get from the M sets, right? Or the M sets that contain alpha? That will be M choose K plus 2. Okay? And this procedure keeps going all the way up to the, well, we don't have to go all the way to N, because the biggest intersection that alpha sits in is an M intersection, not N. So that means we're going to go up to this guy, M choose K, right? And this is going to be M choose all M, like this. Okay. And the sign here is going to follow the same pattern. It's going to be, and again, this is going to be M minus K. Just make sure the signs flip-flop and it lands on the right thing. Okay, so if you someone actually gave you this identity, you could actually argue it this way. So we can imagine that this guy counts basically of M sets, right? And we're looking at the K intersections. Okay, so you got M sets and you're looking at the number of K intersections, and then to contain a certain guy. And then over here, what's happening? Well, then you're looking at, we're going to do the same thing. We're going to look at those M sets and pull out how many K plus 1 intersections we have. And from those K plus 1 intersections, we'll see how many K intersections, right, can be generated from them. So when you multiply these two guys together, this is counting the number of K intersections that we can get when we first pull out the K plus 1 guys and then generate from them the K intersections. Same argument here, same argument here. Only looking at the guys that contain alpha, okay? All right. So what's going to happen here? Well, let's count up the difference here. Let's say this number counts what we want correctly. Then over here, we're going to overcount. But how many ways can you overcount? Because first, you want to look at the number of K guys. So there are M guys out there. Okay. We want to include, so we want to see if there's repetition. So for any given K intersection, right, or a collection of K guys, you can think of it that way, right? Okay. How many guys that are K plus 1 can generate the same K guy over here? Okay, so how do you do that? You go back up here. We need to first put our K guys, whatever they are, right? Place them down. Okay, but now we're looking at what? Well, we have our K guys, right? And then we want to look at, so these are our K guys. We want to look at this extra one right here, right? Because we're looking at all the K plus 1 sets. So this combined will generate the K plus 1 sets. So how many ways can that be done? Well, there are M minus K guys out there, right? Okay. And of the M minus K guys out there, how many are we going to pick out to push this K setup here to K plus 1 setup? We're going to choose 1. Okay? So the number of overcounts here, let me erase this so you get the idea. For this thing is going to be M minus K, choose 1. Now over here, the same thing. So what you do is you pull out the K plus 2 guys, right? And then we generate from them the K guys. Okay. So then, how many ways can this be done? Same argument. All right, so same thing here. So we want to have our K guys, because we're aiming to see redundancy on a specific given K intersection. So here's our guy. Okay. And again, if you remove k of them, you have n minus k out there. How many do we need to pick out to finish this up? We need to pick out 2 to get our k plus 2 guy, right? Okay, so if we do that, it's going to be n minus k, choose 2. And here it's going to be a plus. Okay? Okay, etc. So you can see the argument holds all the way up. When we get to the final one, it's m minus k guys here, right? Again, starting off the same way. But now you need to finish up. You need to flush it all the way out. So we've chosen k guys here. And we're going all the way up to m. If the whole thing should be m, and this is k, then this is m minus k. So this is actually going to be m minus k. Okay? And of course, with the negative 1 to the m minus k. Okay. All right, not a big deal. So again, if it bugs you, we can talk about what this thing means, but that's just a mellow trick. All right, so now, are we done with this? Well, don't forget this term. We got to put this back here. Now, you could write it as 1, but you can also think that, well, if you're looking at a k set, and we've chosen k guys, how many are left over? M minus k. How many are we going to pick out? None of them. That's equivalent to 1, though, right? Okay. Because remember, the guys that are counted here are counted properly. So for any given guy, you're counting him once properly. Okay. But then what does this boil down to? Well, m minus k doesn't change. It's a fixed number, right? All right, so we're basically done. We want to know what does this sum to. So let's rewrite this. So you could definitely see it's the same pattern. It's a fixed guy, and we're letting the bottom go from 0 to 1, and we're alternating signs all the way up to m minus k. So I think we're good. But let's write it like this. N choose, typically we use k, but since k is already taken, let's use a different letter. Let's use like phi, why not, okay? Phi or phi, depending on how you want to pronounce it. So we're going to use this guy. Okay, so now, where's this guy going to go? Well, this part's easy. It's going to go from 0 up to m minus k. But we're going to let n equal m minus k. You don't need to do that. You could put m minus k. It's totally fine. But it's just a fixed number. It doesn't change. And you're going to go from 0 up to that number, right? So it's going to go from 0 up to n. Okay. And we know it's going to alternate. It's going to alternate from what? B. Okay. Because it's going to start at 0 and then go to 1, 2. This works, right? Because negative 1 to the 0 is 1. And then negative 1 to the 1 is negative 1, etc. Positive 1, negative 1, all the way down. Okay. And this guy we know from before, right? From the general pi thing, we know that identity is definitely 0. So we know it works out. So that formula we had up there actually counts it correctly. Now, if you ever have to, bring this back up on command, that's why I like thinking of it this way. It's very mellow. You don't really have to memorize it. Because, again, if you're looking at k sets, right? We're going to start at sk plus 1, and we're going to go all the way up to Sn. Okay. We know the signs are going to alternate, and then we'll talk about this later if you want. This is going to become n minus k. Okay. I get that part. The tricky part is, what about the coefficients? But remember how we argued this, right? We're actually looking at or counting the what? I guess the k intersections. So you want to pick out k guys here. You want to pick out k guys here. But from what? From over here, the k plus 1 intersections. So from the k plus 1 intersections, and from here, from the n intersections. Okay? Meaning the intersections where n guys are intersecting, if that makes sense. Okay. And so this totally works. There is another one that doesn't count exactly the number of elements in k intersections. It actually counts the number of guys that are in k intersections or more. Okay? And that one is actually the true general form of pi, because when you set that k value to be 1, you get pi back. So if you want, we can do that. There is a way of seeing that that's similar to this. Like the way, when I was thinking about it, like how can you put it together? You can't actually visualize it that way. But that one is kind of layered, and it's okay. It's not bad if you want to do it. But I figure like if you convince yourself with this, we can do a much smoother argument. Not super slick because I want to give us some intuition, but there is one that's pretty good that'll use this and basically solve and get the general case. Okay? So we can hopefully do that next time. Please let us know if you have any questions.